Superheterodyne radio receiver, often known in short as a Superhet, was designed to overcome the shortcomings of a tuned radio frequency receiver. It uses a frequency mixer to convert the received radio frequency signal to a fixed and lower intermediate frequency IF signal. It is possible to process the fixed IF signal more easily than widely varying carrier frequencies received from the antenna. The superheterodyne process involves tuning the local oscillator to a frequency which is different from the received signal by as many kilohertz as the intermediate frequency. The process was called superheterodyne because the heterodyne signal, or the difference between the two frequencies, was above the audible range. If the difference in frequencies is lower, you will have an audible beat note. That was how we used to receive CW signals in our broadcast receivers, by heterodyning with a beat frequency oscillator, or BFO. In order to have same IF with varying input signals, the local oscillator frequency is tracked along the intended signal. This is done using a gang capacitor with sets of rotor plates on the same axis. Turning the tuning knob changes capacity in both initial RF filter and the local oscillator to same extent. That is why they are shown as linked with a dotted line in the initial diagram. In the animation, there are 5 sets of rotor plates of different sizes. The gang capacitors which I had used in my projects earlier had only 2 sets. More sets will be needed if you want to tune more circuits, like at the input and output of RF amplifiers in addition. If 2 frequencies are combined in a mixer, the output will have both the sum and difference of the 2 frequencies. The higher frequency, which is the sum of the 2 frequencies, is filtered out by a tuned circuit so that only the difference, known as IF, remains and is sent to further circuits in the radio. Having the subsequent circuits to process a fixed frequency made design simpler than when a whole range of frequencies had to be processed. Standard intermediate frequency used is 455 kHz for common medium wave amplitude modulation AM radios. Usual IF for FM is 10.7 MHz. Licensing authorities will avoid assigning intermediate frequency to broadcast stations to avoid interference in receivers. In the diagram, red parts handle the incoming radio frequency signal, while the green parts handle intermediate frequency. Blue parts handle the detected audio signal. RF amplifier stage is optional. Initial stage is tuned RF stage, which gives initial selectivity and is needed to suppress the image frequency and for prevention of strong out-of-band signals from saturating the initial amplifier. Problem of image frequency is one of the major disadvantages of superheterodyne receiver. Image frequency is an undesired input frequency equal to the station frequency plus or minus twice the intermediate frequency. When a station on image frequency is present, both stations will interfere with each other in the IF stage. This can be prevented by filtering the image frequency in the stages prior to the local oscillator so that it does not produce the same output intermediate frequency in the IF stage. Suppose the IF is 455 kHz, the desired signal is 1000 kHz and local oscillator tuned to 1455 kHz. mixer output will be at 455 kHz. If there is a signal coming in at 1910 kHz, that will also produce an IF of 455 kHz after heterodyning, producing interference. As 1000 kHz and 1910 kHz are sufficiently spaced from each other, the initial RF filter can remove the 1910 kHz signal fairly well and prevent it from reaching the mixer stage. The graphs shown have horizontal axis as frequency. S1 is the intended radio signal. The red graphs show how much of each frequency will pass through the filters. Vertical blue lines in each signal is the carrier frequency with two sidebands on either side. Top graph shows multiple signals received by the antenna. The RF filter effectively removes the image frequency S2, which is beyond its passband. Otherwise, it will produce the same intermediate frequency output in the mixer as it is spaced exactly on the opposite side of the frequency line as the signal S1. LO stands for the local oscillator signal. Mixer also produces output signals on either side of the regular IF because of signals received on nearby frequencies which have passed through the initial RF filter. Signals on either side of S1 which have passed through the initial RF filter will be filtered out at the IF filter stage as it has a narrow pass band. Thus, IF filter output will contain only the desired signal S1, albeit converted to lower frequency. Stages of intermediate frequency amplifier are tuned to a fixed IF and do not change as the receiving frequency changes. This makes the design of IF amplifier simpler. Tuning the IF amplifier for best performance is known as aligning of the IF amplifier. That is done by turning a screw mechanism on top of the IF transformer, like the way you change the value of a preset potentiometer, as well changing the output voltage of a power supply. This needs to be done only once after constructing the Superhet receiver. As the Superhet works at a fixed IF, further adjustments are not needed while receiving each station. Demodulator is a stage which extracts the audio signal from the modulated radio wave. It can be as simple as a diode in case of AM signals, which rectifies the signal into a unidirectional current. The radio frequency component in the output can be shunted to ground using a capacitor of low value, which will not shunt the audio frequency range of the envelope of the wave. In the oscilloscopic view animation shown, the green waves are the radio frequency components and red waves the audio frequency envelope component. Audio frequency is further amplified and fed to the loudspeaker as shown in the initial block diagram. Detection of FM signals is by a discriminator, which is a more complex circuit. CW signals will need a beat frequency oscillator to make them audible. Single sideband signals can also be heard using a beat frequency oscillator, which introduces a carrier back to the SSP signals. In single sideband signals, only one of the sidebands obtained after modulation is transmitted to conserve power and improve efficiency. Carrier and the other sideband are removed. The sideband transmitted can be either the lower sideband, as in frequencies below 10 MHz, or upper sideband for higher frequencies. What remains is mounting this antenna and starting to test SWR tuning All those are tough jobs. I'll do it on another day.